This webcast is a preview of some of the enhancements in the July 2026 APL64 update. The new APL64 Workspace engine is cross-platform, includes the visible property and supports client and server-side debugging. The new Quad HTLC system function supports client actions, and the new Quad HTLS system function supports server actions. Quad EDSS and WriteParen-EDSS, used to edit an APL64 variable in a worksheet form, have some new features. The new GetRecords action for the structured query language database tools, Quad SQLx and ODBC, has been implemented. Applicable system functions now support passive processing of arguments which do not require modification in the result. The new Quad PY and Quad JS system functions support using Python or JavaScript scripts in APL64. The use of APL64 functions in Python or JavaScript scripts using an APL64 cross-platform component, CPC, is fully documented. The Quad WSC system function can render APL64 Workspace content to and from plain text files. Quad SQLx system functions are available for Microsoft SQL Server, IBM DB2, SQLite and MySQL. Quad ODBC supports the legacy ODBC interface for databases like Microsoft Access. In APL64 there are two formats of the APL64 Workspace engine. The Quad WSE-based Workspace engine is and in-process server, whereas the new Quad HTLC and Quad HTLS-based Workspace engine is and out-of-process server. We will be concentrating on the Quad HTLC and Quad HTLS-based Workspace engine here. HTLC is an acronym for Hypertext Listener Client. HTLS is an acronym for Hypertext Listener Server. The Quad HTLC and Quad HTLS-based Workspace engine is cross-platform. The usual exec, pol, polisync, get_sysvar, getVar, load WS, set_sysvar, setVar, syscall, syscommand actions are supported. These actions are requested by Quad HTLC and carried out on the Quad HTLS server side. The Quad HTLC and Quad HTLS-based Workspace engine provides a visible property for the server side. The Quad HTLC and Quad HTLS-based Workspace engine supports debugging of the client and server sides. The Quad HTLC and Quad HTLS-based Workspace engine, because it is and in-process server, requires no serialization of input and output between the client and the server. To learn all about the Quad HTLC and Quad HTLS-based Workspace engine, read the Using Quad HTLC and Quad HTLS document in the APL64 Developer Version Help menu. All the actions are fully documented. Examples which you can copy and run are also provided. The Quad HTLC URL system variable is used to select the URL for communication between the client and the server. The URL can contain a port number, for example, http://localhost 65001. The URL can use HTTP or HTTPS. The Quad HTLC listen local action creates a local HTLS server which is exclusive to the Quad HTLC instance which created it. Use the Quad HTLC listen URL action to create a shared HTLS server. Because the Quad HTLC visible property is true by default, the HTLS server instance of APL64 is visible. The requests made by the client using Quad HTLC are reflected as actions on the HTLS server side. The HTLS server is an APL64 workspace engine for the exclusive use of the HTLS client in this example. The result of HTLC actions which affect the server is a vector. The first element of the vector is a Boolean indicating if the requested operation succeeded. The second element of the vector is an empty character vector if the requested operation succeeded, or the exception message if it failed. The third element is optional, and is present only if the requested server-side operation yielded a result. The vector format of the result of HTLC actions was selected because the alternative is using try-catch on the HTLC client side, which is an expensive operation. Because the HTLC client and HTLS server are independent APL64 instances, the visible HTLS server can be debugged just like the HTLC client side. The HTLC client can use the HTLC timeout action to specify how long the HTLC client will wait for the HTLS server to respond. In production mode, when the application is using runtime instances of APL64, workspace engines can be created, but they cannot be made visible or debugged, since the APL64 runtime does not include the APL64 developer session. A summary of HTLC actions is available using the HTLC help action. Refer to the user documentation of Quad HTLC in the APL64 developer version for more details and working examples. The HTLC exec action will run an APL64 executable statement on the HTLS server and return the result, if any, to the HTLC client. The HTLC call async action makes a request to run a server-side APL64 function, but does not wait for the result. The result of the HTLC call async action is returned to the HTLC client as an event which is handled by a client-side APL64 function. The HTLC call async action can be used to request function executions in parallel on an HTLC server. The HTLC load workspace action will load a pre-existing workspace on the server machine to the HTLS server on that machine. APL64 variables on an HTLS server can be created and modified using the HTLS variable action. The HTLC listen local action can be used to create one or more HTLS workspace engine instances which are exclusive to that HTLC server. The HTLC getServer log will return the log events which apply to this HTLC server. A summary of HTLS actions is available using the HTLS help action. Refer to the user documentation of Quad HTLS in the APL64 developer version for more details and working examples. The HTLS listen action can be used to create a shared HTLS server. The HTLS listen action supports the HTTP and HTTPS protocols. The HTLS log file options action controls the path, set to empty for no logging, maximum size of current log archive, number of log archives, and if the log file header is included. The HTLS log is in CSV format. The HTLS log columns are timestamp, thread ID, client ID, and message. The APL64 HTLS workspace engine is a cross-platform, out-of-process server using the HTTP protocol. The APL64 Quad WSE workspace engine is a cross-platform, in-process server which requires no endpoint serialization. The APL plus Win APLWS engine can be created as a Windows-only, out-of-process or in-process server which requires the deprecated ActiveX endpoint serialization. Endpoint serialization reduces performance of a workspace engine. APL64 programmer provided examples were helpful for the APL64 development team to achieve these performance improvements. Your results may vary, so perform your own tests. Keep sending performance questions with sample data to the APL64 development team. Use QuadMF and QuadProfile to evaluate performance. Editing of APL64 variables in worksheet format is available in the APL64 developer version using the EDSS system function and system command. In this version of APL64, the AutoFit range menu item has been implemented to autofit all or selected worksheet rows or columns. The new GetRCDS action returns the specified number of records up to the number of available records in the record set. The GetRCDS action is an alternative to returning all records or looping to return a list of records. The APL64 system functions QuadLJust, QuadRJust, QuadSS2Mat, QuadRound, QuadUCase, QuadLCase now passively process arguments which are inapplicable, instead of throwing and exception. We noticed in customer-provided code that a try-catch envelope was used around these system functions to effectively passively process inappropriate arguments. Using try-catch is expensive, so building passive processing into these system functions improves application performance. The new APL64 QuadPy and QuadJS system functions can be used to run Python or JavaScript scripts within an APL64 function. The table displayed lists a description of available actions and which yields a result as well as which system function supports the action. The new APL64 QuadPy system function can be used to run Python scripts in APL64. The APL64 QuadPy system function can create an instance of the Python engine within the current APL64 interpreter instance. The Python engine created using QuadPy persists during the entire APL64 instance. When an APL64 instance is closed, the Python engine, if any, is disposed. The QuadPy exec action can execute a Python script. The QuadPy eval action, with synonym QuadPy get, can obtain the value of a Python expression. The QuadPy set action can set a Python variable value with an APL64 value. The QuadPy exec, eval, get and set actions support value substitution, so that APL variable values can be used a Python script or expression. The new APL64 QuadPy system function can be used to run Python scripts in APL64. The examples shown here demonstrate evaluating a Python expression and executing a multi-line Python script. The new APL64 QuadJS system function can be used to run JavaScript scripts in APL64. The APL64 QuadJS system function can create an instance of the JavaScript engine within the current APL64 interpreter instance. The JavaScript engine created using QuadJS persists during the entire APL64 instance. When an APL64 instance is closed, the JavaScript engine, if any, is disposed. The QuadJS exec action can execute a JavaScript script. The QuadJS eval action, with synonym QuadJS get, can obtain the value of a JavaScript expression. The quad.js setAction can set a JavaScript variable value with an APL64 value. The quad.js exec, eval, get and set actions support value substitution, so that APL variable values can be used to JavaScript script or expression. The new APL64 quad.js system function can be used to run JavaScript scripts in APL64. In the example illustrating the execution of a multi-line JavaScript, execution control is transferred between APL and the JavaScript engine within the JavaScript script, using the APL:\line prefix. The documentation in the APL64 developer version provides information and examples which illustrate how APL64 functions can be used in Python and JavaScript applications. The APL64 functions are defined within an APL64 CPC, cross-platform component. An APL64 CPC is a .NET NuGet package which can be used in Python and JavaScript. Plain text files containing only functions, method, are the basis of modern code repositories, such as GitHub. The new APL64 quad.WSC system function can emit a plain text file from APL64 Workspace functions, and can perform the inverse operation to materialize a plain text file to APL64 Workspace functions. All or selected functions in a workspace can be rendered to a plain text file. All or selected function representations in a plain text file can be materialized to functions in an APL64 workspace. Line 6 of this example shows how to render all functions in the workspace to plain text representations using the quad.WS CPC, prepare content, action. Line 18 of this example then expunges all functions in the workspace. Line 22 of this example shows how to materialize all plain text function representations to functions in the workspace using the quad.WS CMC, materialize content, action.